So, here's something that might catch you off guard. Black holes, which most people picture as some kind of cosmic drain, some terrifying void swallowing everything nearby, a thing to be kept at a safe distance in science fiction plots. Black holes are not actually holes. They're not empty. And in a very real, physically precise sense, they're not even dark. What they are is something much stranger, and in some ways much more beautiful than the standard image suggests. And the path to understanding what they really are starts not with a giant telescope or a particle accelerator, but with a question about falling. Just falling. What do you feel when you fall? That question, as simple and as physical as anything you've ever experienced in your own body, turns out to be one of the most productive questions in the history of science. And we're going to follow it tonight all the way from a man imagining himself dropping off a rooftop in 1907 to the moment a century later, when scientists on Earth heard two black holes collide 1 billion light-years away. We're going to take this slow, because the ideas deserve that. None of this requires you to be a physicist. It requires you to be curious and willing to let go of some assumptions you've probably been carrying without knowing it. Assumptions about what space is, about what time is, about what it means for something to pull on something else. We're going to loosen all of those, gently. And what you find underneath them is something so strange and so elegant that once you've seen it, you can't quite unsee it. Let's start with a man who spent 10 years trying to extend a theory he'd already finished. In 1905, Albert Einstein, 26 years old, working days as a patent examiner in Bern, Switzerland, published 4 papers in a single year that each would have been enough to secure a place in the history of physics. One of them introduced special relativity. The core idea was that the laws of physics look identical to any observer moving at a constant velocity, no matter what that velocity is. And that the speed of light specifically is the same for every such observer regardless of how fast they're moving toward or away from the source. These two postulates together implied that time runs differently for observers in relative motion. That length's contract. That simultaneity is not universal. It was an extraordinary achievement and it transformed physics almost immediately. But Einstein already knew it wasn't enough. Special relativity had a built-in limitation and he was uncomfortably aware of it. It applied only to a very specific kind of motion. Steady, constant velocity motion. The moment you introduced acceleration, the moment you tried to deal with things speeding up or slowing down or changing direction, special relativity went quiet. It had nothing to say. And the force responsible for nearly all the acceleration in the everyday universe, the thing that keeps your feet on the floor and the moon in orbit and the planets circling the sun, gravity. Special relativity had nothing to say about that either. Even worse, Newton's description of gravity, which had worked spectacularly well for over 2 centuries, was deeply incompatible with what Einstein had just established. Newton described gravity as an instantaneous force acting across any distance, no matter how vast. But Einstein had just shown that nothing, no signal, no effect, no information of any kind can travel faster than light. The two theories were flatly contradicting each other, and Einstein knew he would have to resolve that contradiction. What he didn't know was that doing so would take another 10 years and would require him to abandon some of the most fundamental assumptions in all of physics. The first crack, the one that let the light in, came in 1907, and Einstein would later describe the moment it arrived as the happiest thought of his life, which is a striking thing to say about imagining yourself plummeting off a building. But that's essentially what happened. He was sitting at his desk at the patent office thinking about gravity, and a thought arrived. If a person falls freely under gravity, they feel no weight. Not reduced weight, not diminished weight. No weight at all. We've all experienced a version of this, that brief stomach-lifting moment at the top of a roller coaster, or the momentary floating sensation when an elevator drops suddenly. Expand that into a full free fall, and it generalizes completely. Astronauts in orbit are not weightless because there's no gravity where they are. There's plenty of gravity up there. The Earth's gravitational pull extends far beyond the atmosphere. They're weightless because they're in free fall. The International Space Station and everyone inside it is continuously falling toward the Earth. It just keeps missing because it's also moving sideways fast enough that the curvature of Earth keeps falling away beneath it. But the experience of weightlessness inside that station is the same as if there were no gravity at all. You couldn't tell the difference. That's what Einstein saw. That a person falling freely in a gravitational field is, from their own point of view, in a situation physically indistinguishable from being in empty space with no gravity at all. And if that's true, then gravity can't be a force in quite the ordinary sense, because forces leave a trace. They push on things, they accelerate things, you can feel them, but free fall erases the trace. You feel nothing. So what is gravity actually doing if not pushing and pulling in the conventional sense? Einstein called this the equivalence principle. And before we go further, let's really sit with what it says, because it's easy to nod along to it and miss how radical it actually is. The principle says that being at rest in a gravitational field and accelerating upward through empty space are locally indistinguishable. Completely equivalent. Not approximately equivalent. Not equivalent for practical purposes. Equivalent in the sense that no experiment you could perform inside a sealed room would tell you which situation you're in. If you're standing in a box and you feel weight pressing your feet into the floor, either you're sitting on the surface of a planet with gravity pulling you down, or you're in a rocket in deep space with an engine pushing the floor up into you. No measurement you can make inside that box will settle the question. The two situations are physically the same. And if they're the same, then anything you know about acceleration applies to gravity, and vice versa. That's the skeleton key to everything that follows. Here's one place to see what that key unlocks. Imagine you're in that accelerating rocket. A beam of light comes in through a tiny hole in the side wall and travels horizontally across the cabin. While the light is crossing, the rocket is accelerating upward. By the time the light reaches the other wall, the rocket has moved up a little, so the beam hits the far wall slightly lower than where it entered. From inside the rocket, the light path curves downward. It bends. Now apply the equivalence principle. Acceleration and gravity are locally equivalent. So if the light bends in the accelerating rocket, light must also bend in a gravitational field. The gravity of a massive object like the sun should deflect a beam of light passing near it, curving its path. And the amount of deflection isn't arbitrary. Once you have the full theory, you can calculate it precisely, which is exactly what made this prediction so powerful when the time came to test it. But we're getting ahead of ourselves. Because in 1907, Einstein had the equivalence principle and a rich intuition about where it pointed, but he didn't yet have a mathematical language capable of expressing it, and finding that language would consume the next 8 years of his life. The central conceptual leap, the one that separates general relativity from everything that came before it, is this. Gravity isn't a force transmitted through space. Gravity is the geometry of space itself, or, more precisely, of space-time. Mass and energy don't reach across the void and tug on distant things. They warp the shape of the four-dimensional fabric of the universe, and other objects respond by following the natural curves of that fabric. What looks to us like a gravitational force, the pull that makes an apple fall and keeps the planets in their orbits, is actually just free motion through curved space-time. The apple isn't being yanked downward, it's following the straightest possible path through a space-time that the Earth's mass has curved in its vicinity. There's no force, there's just geometry. This is one of those ideas that either clicks immediately or doesn't, so let's work at it from a different angle. Imagine the surface of the Earth drawn on a flat sheet of paper, and two people starting at the equator, separated by some distance, and walking due north. On a flat surface, they'd be walking parallel lines, and they'd stay the same distance apart forever. But on a sphere, walking due north means walking along great circle lines, and great circles on a sphere converge. The two people, each walking in what they experience as a perfectly straight line, will find themselves getting closer and closer together, and eventually meeting at the North Pole. If you didn't know the surface was curved, you might say some force was pulling them together. But there's no force. There's just the curvature of the surface making paths that appear straight on the surface, converge in 3 dimensions.
Your feet, which are a little closer to the Earth's center than your head, are aging very slightly more slowly than your head. Over a lifetime, the difference amounts to something like 90 billionths of a second, which is not very much. But the principle matters because there are situations where the gravitational time dilation is not negligibly small. And we'll come to those. So Einstein had the equivalence principle in 1907. A profound physical insight suggesting that gravity isn't a force transmitted through space, but something intimately connected to the geometry of space and time themselves. And he had specific qualitative predictions. Light bends near massive objects. Time runs more slowly in stronger gravitational fields. Both followed directly from the equivalence principle with relatively simple reasoning. But here's the gap. Having a physical insight is not the same as having a physical theory. A theory needs to be precise. It needs to give you numbers, not just directions. It needs to tell you not just that light bends near the sun, but by exactly how much. It needs to give you equations that you can solve to find the orbit of a planet or the path of a light beam, or the rate at which a clock ticks at a given distance from a given mass. Einstein's insight in 1907 was brilliant. But turning it into a complete mathematical theory was going to require something he didn't yet have. The gap, and this is important, was a mathematical one. The physics was pointing at something. The equivalence principle was saying, gravity is connected to the geometry of space and time. That mass and energy somehow warp the fabric of the universe, and that objects respond to that warping by moving along the natural curves of the fabric. That what we call gravitational attraction is actually just free motion through a curved space-time. It's a beautiful and coherent picture. But describing it mathematically, writing down equations that precisely specify the curvature at every point and tell you how objects move through it, that requires a branch of mathematics that wasn't part of the physics curriculum in the early 20th century. It was the mathematics of curved surfaces and curved spaces. What mathematicians call differential geometry. And specifically the formidable apparatus developed in the 19th century by a German mathematician named Bernhard Riemann. Riemann was one of those figures who seems, looking back, to have been working on exactly the right problem at exactly the wrong time. He died in 1866 at the age of 39, and the full implications of his mathematical work were not understood for decades. But what he had built was a comprehensive framework for describing the geometry of curved spaces of any number of dimensions. Not just the familiar two-dimensional curved surfaces, like the surface of a sphere, but curved spaces of 3 dimensions, 4 dimensions, as many dimensions as you needed. He gave mathematicians the tools to calculate distances, angles, curvatures, and geodesics, which are the generalization of straight lines to curved spaces in any such space. He didn't know what this mathematics would be used for. He was doing pure mathematics, following the internal logic of geometry wherever it led. And it led somewhere that would become, half a century after his death, the essential language of the most ambitious theory of physics ever constructed. Einstein came to Riemannian geometry through his friend Marcel Grossmann. Grossmann had been Einstein's closest companion during their student years at the Swiss Federal Polytechnic in Zurich, the ETH, a quietly brilliant mathematician who had been responsible in no small part for Einstein surviving his exams. Einstein was not a conventional student. He was clever, charming, curious, and frequently absent. He skipped lectures, angered professors, and found the structured curriculum more irritating than illuminating. Grossmann was the opposite. He attended everything, took meticulous notes, understood the material deeply, and he let Einstein borrow those notes to catch up before examinations. So in a real sense, Grossmann had already bailed Einstein out once. In 1912, when Einstein was a professor in Zurich and becoming increasingly desperate to find the mathematical framework that could express his gravitational ideas, he turned to Grossmann again. The story goes that he showed up at Grossmann's door and said something to the effect of, "You have to help me or I'll go crazy." And Grossmann, who had just accepted a professorship in mathematics at the ETH, recognized immediately what kind of mathematics Einstein was looking for. He pointed him toward Riemann, toward the tensor calculus that allowed precise mathematical operations in curved spaces regardless of what coordinate system you used. And that was the opening. Together, Einstein and Grossmann worked through the problem of gravitational field equations, the mathematical relationship that would connect the distribution of matter and energy in the universe to the resulting geometry of spacetime. They published a preliminary paper in 1913 called the Entwurf, which means outline or draft in German. It was close to the right answer, but it wasn't there. The equations in the Entwurf had a problem. They weren't what physicists call generally covariant, meaning they didn't maintain their form under all possible coordinate transformations. Einstein wanted equations that would look the same to any observer regardless of how they chose to describe their coordinate system, that would be equally valid in any reference frame no matter how it was moving or rotating. That was the physical demand of the theory, and the Entwurf equations didn't satisfy it. Einstein knew this. He convinced himself through a complicated argument he called the whole argument, which turned out to be flawed, that fully covariant equations were actually impossible. And so he spent nearly 2 years, 1913 and most of 1914, working with equations he suspected were wrong, unable to see past the flaw in his own reasoning. It was a particularly painful kind of intellectual trap. He was close enough to smell it, too far away to reach it. Meanwhile, the world was changing around him in ways that made the urgency feel personal. The summer of 1914 brought the outbreak of the First World War. Einstein was living in Berlin by then, having accepted a prestigious position at the Prussian Academy of Sciences and a professorship at the University of Berlin. He had just separated from his first wife Mileva, a separation that was bitter and complicated and that cost him time and emotional energy he could barely spare. His health was poor. He was thin, often exhausted, working under conditions of physical and psychological stress that would have derailed a lesser person. And he was, during all of this, still trying to find the right equations. Still spending every hour he could steal from administrative duties and lectures and personal difficulties on the problem of general relativity. Then 1915 arrived, and with it a kind of crisis and a kind of breakthrough that are inseparable from each other. The crisis came in the form of David Hilbert. Hilbert was arguably the greatest mathematician alive. He was based at Göttingen, a city that was at the time the mathematical capital of the world, and he had spent his career establishing himself as a thinker of almost frightening range and power. He had reorganized the foundations of geometry, contributed to number theory, mathematical physics, and logic in ways that reshaped each field. He was 63 years old in 1915, which for a mathematician is an age at which most original work is behind them, but Hilbert was still very much operating at the frontier. In the summer of 1915, Einstein gave a series of lectures in Göttingen, and Hilbert attended. And he became, almost immediately, fascinated by the problem of finding the gravitational field equations. He began working on it himself. He had mathematical tools that Einstein was still learning. Variational methods, Lagrangian formalism, ways of deriving equations from underlying principles of elegance and economy that could bypass some of the computational brute force that Einstein was relying on. And he was fast. So in the autumn of 1915, you have a situation that is simultaneously a collaboration and a race. Einstein in Berlin, Hilbert in Göttingen, exchanging letters that shift between collegial and tense. Einstein sharing some of his progress, Hilbert sharing some of his, both of them aware that whoever arrived at the correct field equations first would have accomplished one of the supreme acts of theoretical physics. And Einstein was terrified. Not just of losing priority, though he cared about that and shouldn't be blamed for caring about it. This had been his vision, his decade of struggle, his theory. He was terrified because he could see that Hilbert, approaching the problem fresh, with better mathematical tools and without Einstein's accumulated wrong turns, might actually get there faster. What followed, in November 1915, is one of the most extraordinary months in the history of science. Einstein presented a paper to the Prussian Academy of Sciences on November 4th with new field equations, more general than the Entwerf equations, but still not quite right. He revised and presented again on November 11th. And then something happened on November 18th that probably saved the theory. He applied his still incomplete equations to a problem that had been nagging at astronomers for 60 years. The anomalous precession of Mercury's perihelion. Let's pause on that, because it's one of those moments that deserves its full drama. Mercury is the innermost planet, the one closest to the Sun, and its orbit is an ellipse. But the ellipse is not fixed. The long axis of the ellipse rotates slowly around the Sun over time, a motion called precession. Most of this precession is accounted for perfectly by Newtonian gravity, the combined effect of the gravitational tugs from all the other planets. But when astronomers subtracted out everything Newtonian gravity could explain, there was a leftover, a stubborn discrepancy of 43 arcseconds per century. An arcsecond is 1/3600th of a degree, so 43 arcseconds is a tiny angle, but the measurement was precise and the discrepancy was real. Urbain Le Verrier, the same French astronomer who had predicted the existence of Neptune by noticing irregularities in Uranus's orbit, had pointed out Mercury's anomalous precession in the 1850s. And for 60 years, nobody had a satisfactory explanation. Some proposed that there was another planet, even closer to the Sun, that was pulling Mercury's orbit slightly out of shape. They named it Vulcan and searched for it for decades. It wasn't there. The anomaly persisted, unresolved, a small thorn in the side of Newtonian gravity. Einstein plugged the numbers for Mercury's orbit into his November equations. And the answer came back 43 arcseconds per century. Exactly. He later told a friend that when he saw the result, his heart palpitated. He was so excited he couldn't work for 3 days. Think about what that moment must have felt like. 8 years of struggle, wrong turns, self-doubt, competition from the greatest mathematician in the world. And then the universe handing you this perfect gift. A number that matches an unexplained anomaly to the decimal point, a problem that had been sitting unresolved since before you were born, solved without any adjustable parameters, falling out naturally from equations you derived from first principles about the nature of space and time. In that moment, Einstein knew. Not approximately. Not probably. He knew. 1 week later, on November 25, 1915, Einstein presented the complete field equations of general relativity to the Prussian Academy. These are the equations that bear his name. They are sometimes written in a beautifully compact form that can fit on a single line, though that compactness conceals an enormous amount of mathematical structure. On one side of the equal sign, you have a tensor describing the curvature of space-time at every point. On the other side, a tensor describing the distribution of matter and energy. The equation says these are proportional. Mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. That's it. That's the whole theory in one sentence. And those two ideas, sitting across an equal sign, contain within them predictions that would take a century to fully test and that are still being tested today. Hilbert, for his part, submitted a paper to a journal on November 20th, 5 days before Einstein's final presentation, containing field equations in a form derived from his variational approach. The question of priority, who got there first, has been debated by historians ever since. What we know is that the physical conception, the equivalence principle, the geometric picture of gravity, the decade of development, the physical interpretation of the equations, all of that was Einstein's from the beginning. Hilbert himself later acknowledged this. He reportedly said that every boy in the streets of Göttingen understands four-dimensional geometry better than Einstein does, and yet it was Einstein, not the mathematicians, who did the work. Which is a generous assessment from a man who was also trying to reach the same finish line. The modern consensus gives Einstein clear priority for the physical theory while acknowledging that Hilbert derived the equations independently and elegantly from different starting assumptions. It's one of those historical situations where the credit question is genuinely complicated by the fact that two brilliant people were thinking about the same problem at the same time, and the universe only has one answer. So by the end of November 1915, general relativity existed. But having the equations is not the same as knowing what they predict. The field equations of general relativity are 10 coupled nonlinear partial differential equations. Nonlinear is the key word. In linear equations, solutions can be combined. If you have two solutions, their sum is also a solution. Nonlinear equations don't work that way. Solutions don't add up simply. The mathematics of finding exact solutions to these equations is ferociously difficult, and Einstein himself could only work with approximations. He was genuinely not sure whether exact solutions could be found for physically interesting situations. He was answered within months. In December 1915 and January 1916, a German physicist and astronomer named Karl Schwarzschild was stationed on the Eastern Front of the First World War, serving in the German artillery. He was calculating trajectories for artillery shells during the day and reading Einstein's papers in whatever time he could find. And he found an exact solution. The first exact solution anyone had found to the field equations of general relativity. The solution describes the spacetime geometry around a perfectly spherical, non-rotating, electrically uncharged mass. Not approximately. Exactly. He sent the results to Einstein in 2 letters, one in late December and one in early January, and Einstein presented them to the Prussian Academy. He told Schwarzschild, delighted that the equations yielded to such exact treatment. Schwarzschild died in May 1916, probably from a disease contracted on the Eastern Front. He was 42 years old. The solution that carries his name, and the object it describes, would turn out to be among the most consequential results in the history of physics. Now let's look at what the Schwarzschild solution actually says, because it contains something strange. For any spherical mass, the solution defines a particular radius, a particular distance from the center of the mass, at which the mathematical description of the spacetime geometry does something peculiar. Certain quantities in the solution become infinite at this radius. For ordinary objects, this radius is irrelevant in practice. For the Sun, the Schwarzschild radius is about 3 kilometers. But the Sun's actual physical surface is nearly 700,000 kilometers from its center. The Schwarzschild solution only applies in the vacuum outside the mass, so for the Sun, the problematic radius is buried deep inside the Sun's body where the solution doesn't apply. Same for the Earth. The Earth's Schwarzschild radius is about 9 millimeters, buried under 6,000 kilometers of rock and mantle and metal. Completely academic. But the question that the solution raised, and that would simmer uneasily for decades, was this. What if you had an object so dense, so compressed, that its physical size was smaller than its own Schwarzschild radius? What would happen at that critical distance? Was the behavior of the mathematics at that point a real physical phenomenon, or was it an artifact of the coordinate system, the way that maps of the globe get distorted near the poles without anything actually being strange about the poles themselves? Einstein and most of his contemporaries assumed it was an artifact. They assumed nature would find some way to prevent any real physical object from being compressed to its Schwarzschild radius. That assumption would hold for about 20 years. And then it began to crack. The cracking started in 1939, in an unlikely place. J. Robert Oppenheimer, who would later lead the Manhattan Project and become one of the most morally complicated figures in 20th century science, published a paper with his graduate student Hartland Snyder analyzing what happens when a sufficiently massive star exhausts its nuclear fuel. The paper showed for stars above a certain mass threshold, the collapse of the core was unstoppable. The pressure of nuclear reactions and the quantum mechanical resistance of densely packed matter, which could halt the collapse of lower mass stars into neutron stars, was simply insufficient. For these more massive collapsing stars, there was nothing to stop the implosion. The mathematics showed the collapse continuing past the Schwarzschild radius and beyond. And Oppenheimer and Snyder's paper described what happened in that case. The collapsing object would, from the perspective of an outside observer, appear to slow down and freeze at the Schwarzschild radius, the light from its surface becoming increasingly redshifted and dim, fading asymptotically toward darkness but never quite reaching it. While from the perspective of someone on the surface of the collapsing star, the collapse would continue through the Schwarzschild radius and down to a singularity in a finite and not very long proper time. The two descriptions are not contradictory. They are just views from different vantage points, each valid in its own reference frame, but the paper was largely ignored. The Second World War was beginning. Oppenheimer would soon be consumed by the Manhattan Project. And the physics community as a whole was in the process of shifting its attention toward quantum mechanics and nuclear physics, where the exciting discoveries were piling up faster than anyone could process them. General relativity was still regarded as beautiful, probably correct, but remote from experimental reach and somewhat irrelevant to the practical concerns of physics in the middle of the 20th century. This period, roughly 1920 to 1960, is sometimes called the low water mark of general relativity. It was pursued by a relatively small community of researchers, it generated few dramatic experimental tests, and it sat somewhat at the margins of the physics world. Some people half-jokingly called it a backwater. Then the 1960s arrived and changed everything. New observational technologies, radio telescopes and X-ray detectors aboard rockets and early satellites began revealing objects in the sky that didn't fit into the established categories. Quasars, sources of radio waves so powerful they outshone entire galaxies, apparently emanating from points too small to resolve with any instrument. X-ray binaries, systems in which two objects orbited each other and one of them was emitting prodigious quantities of X-rays, suggesting extreme temperatures and densities. And theorists began revisiting the question that Oppenheimer and Snyder had raised in 1939 and then walk away from. Was the collapse of massive stars really unstoppable? And if it was, what exactly was the endpoint? The answer, and the rigorous proof of it, came from a British mathematician named Roger Penrose. In 1965, Penrose published a paper of extraordinary power and economy. It was only a few pages long, but it contained an idea that transformed the field almost immediately. He introduced what he called trapped surfaces, a topological concept describing regions of space-time from which even outward-directed light cannot escape because the curvature is so severe. And he proved, under very general conditions, that once a collapsing body develops a trapped surface, the formation of a singularity is not merely possible but inevitable. The proof didn't depend on perfect spherical symmetry or any other idealizing assumption. It worked for realistic, messy, asymmetric collapses. Nature had no escape. Once the threshold was crossed, the singularity formed. Period. This was a qualitative change in how physicists thought about the consequences of general relativity. It wasn't a speculation anymore, or a suggestion from a particular solution in a particular idealized case. It was a mathematical theorem. Penrose was awarded the Nobel Prize in Physics in 2020 for this work 55 years after it was published. Which says something, both about the timescale on which deep ideas are recognized and about the longevity of Penrose's contribution. The term black hole itself was popularized a few years after Penrose's paper by the American physicist John Wheeler, who had a gift for language that most theoretical physicists lack. Wheeler was also responsible for a number of other memorable phrases in physics. He coined wormhole and it from bit, and was in general someone whose ideas were always worth listening to even when they were speculative. Before Wheeler's popularization, these objects had been called various things. Frozen stars, collapsed stars, Schwarzschild singularities. The name black hole caught on because it captured the essential physics so vividly. A region of space from which nothing returns. And now, decades after Oppenheimer and Snyder and Penrose, we had the theoretical framework. We understood that stellar mass black holes should form when sufficiently massive stars die, that they were not exotic speculations but natural consequences of the same physics that governed ordinary stellar evolution. The question was whether we could actually find them. The answer began coming in the 1960s and 1970s through indirect methods. If a black hole has a companion star, the black hole's gravity will pull material off the star's outer layers, and this material forms a swirling disk around the black hole before spiraling in. As the material spirals inward, it is compressed and heated to extraordinary temperatures and emits X-rays. So X-ray binaries, systems of two objects in orbit where one is producing bright X-ray emission, became the primary hunting ground. Cygnus X1, discovered in 1964, became the first WID accepted black hole candidate. The X-ray source was matched to a visible star, a massive blue supergiant, and the orbital dynamics of the binary system revealed that the invisible companion had to be far too massive to be a neutron star. The mass was in the range where only a black hole was consistent with everything we knew about dense matter. Stephen Hawking famously bet the physicist Kip Thorne that Cygnus X1 was not a black hole. He conceded the bet in 1990 as the evidence became overwhelming. He had hedged himself, he said, in case everything he'd worked on was wrong, because if black holes didn't exist, he'd at least have the consolation of winning the bet. But indirect evidence is a different thing from direct detection. And the physics community had been building toward two kinds of direct detection for decades. The first was gravitational waves. The second was imaging the shadow of a black hole. Both required technology that took generations to develop. And both arrived within 4 years of each other in what was one of the most extraordinary experimental periods in the history of physics. Let's take the gravitational waves first, because they lead somewhere particularly deep. Einstein had predicted gravitational waves almost immediately after completing the field equations in 1915. The equations implied that accelerating masses should produce ripples in the fabric of spacetime, disturbances that would propagate outward at the speed of light in every direction, stretching space in one direction while compressing it in the perpendicular direction, exactly the way an electromagnetic wave oscillates electric and magnetic fields. The prediction made sense in the theory. But Einstein was pessimistic about whether such waves could ever be detected. He calculated the amplitude of the waves you'd expect from any physically realistic source, and the numbers were discouraging. Even the most violent events imaginable, colliding stars, exploding supernovae, would produce ripples in the space-time fabric so faint by the time they reached Earth that detecting them seemed essentially impossible. Einstein apparently said at various points that the waves would never be detected, that the technology required simply could not be built. He was wrong about that, but the skepticism wasn't unreasonable given the scales involved. To understand why detecting gravitational waves is so difficult, you need to understand what they actually do. A gravitational wave passing through your body right now would alternately squeeze you slightly in one direction and stretch you slightly in the perpendicular direction. The squeezing and stretching would happen at the frequency of the wave, which for waves from compact binary systems like two neutron stars orbiting each other is in the range of tens to hundreds of cycles per second, similar to the frequency range of audible sound. The amplitude, the fractional change in length caused by the wave, is what's vanishingly small. For a wave from a typical astrophysical event 100 megaparsecs away, a distance of roughly 300 million light-years, the fractional length change is on the order of 10 to the minus 21. That's a number with 20 zeros after the decimal point before you get to the 1. Applied to a ruler 1 meter long, that's a length change of 10 to the minus 21 meters. For comparison, a proton is about 10 to the minus 15 meters across. So you're trying to measure a change in length that is 1,000,000 times smaller than the diameter of a single proton. It is not immediately obvious that this is even conceptually possible, let alone practically achievable. And yet it is. The key insight that made it possible is that what you actually need is not to measure an absolute length but to measure a change in the ratio between two lengths. If you have two perpendicular arms and a gravitational wave is passing through, one arm gets slightly longer while the other gets slightly shorter, and then they trade roles as the wave continues. If you can measure that differential change, that difference in length between two arms, you can detect the wave. And the tool for measuring minute differences in length between two light beams is the interferometer, a device that has been used in precision measurement since the 19th century when Michelson and Morley used one to show that the speed of light was the same in every direction, which as we said earlier was one of the key experimental results that special relativity was built to explain. The principle of a modern gravitational wave interferometer is not too different from Michelson's original device, though the engineering required to reach the necessary sensitivity is almost incomprehensibly more sophisticated. You split a laser beam into two beams traveling at right angles to each other. Each beam travels down a long arm, bounces off a mirror at the end, and returns to the starting point. The two returning beams recombine and interfere. If the two arms are exactly the same length, the interference is perfectly destructive and no light reaches the detector. If one arm is very slightly longer than the other, the interference is not perfectly destructive and a tiny amount of light reaches the detector. The amount of light you detect tells you how different the two arm lengths are. Gravitational waves passing through the device would make the two arms alternately longer and shorter relative to each other, and you'd see a corresponding signal in the lie. The challenge is that every other possible source of length change, every vibration, every seismic tremor, every thermal fluctuation in the mirrors, every quantum fluctuation in the laser light itself, is also a source of signal that you have to distinguish from a gravitational wave. Building an instrument sensitive enough to see a length change of 10 to the minus 21 meters while keeping every other source of noise below that threshold is an engineering problem of staggering proportions. It took the LIGO project, the Laser Interferometer Gravitational Wave Observatory, decades of development and many intermediate stages of instrument design. The final version that made the first detection had arms 4 kilometers long. It operated the mirrors in no perfect vacuum to prevent the laser beams from being disturbed by air molecules. The mirrors themselves were polished to a smoothness measured in fractions of a nanometer and suspended on elaborate pendulum systems to isolate them from ground vibrations. The laser was carefully engineered to reduce quantum noise in the light. Hundreds of physicists and engineers over many years built, calibrated, and operated instruments in Louisiana and Washington state, waiting for the universe to shake them. On September 14, 2015, at 5:51 in the morning Eastern Daylight Time, it did. The signal was in the detector for about 0.2 of a second. It swept upward in frequency from about 35 Hz to about 150 Hz, a chirp, the sound the universe made when two black holes finished a dance that had been going on for billions of years and finally merged into one. You can actually play the signal as audio, sped up into the audible range, and it sounds like a brief rising chirp, a soft thump, which is perhaps the most understated possible description of an event releasing more energy than all the stars in the observable universe combined. The two black holes that merged were each roughly 30 solar masses. They had been orbiting each other for a very long time, slowly spiraling inward as they lost energy to gravitational waves. In the final fraction of a second before the merger, they were moving at a substantial fraction of the speed of light, and the gravitational wave power they were emitting was enormous. The wave reached Earth after traveling roughly 1.3 billion light-years. By the time it arrived, the space-time distortion it carried was on the order of 10 to the minus 21, exactly in the range the instrument was designed to detect. The Louisiana detector and the Washington detector both registered the signal, separated by about 7 milliseconds, consistent with the wave arriving first in Louisiana and then in Washington at the speed of light. The waveform matched the predictions of general relativity, calculated from the theory of two merging black holes, not approximately, not roughly, with striking precision. The scientists working on LIGO had, naturally, protocols for these moments. You don't announce the detection of gravitational waves casually. The instrument had been through many years of searching without a confirmed detection, and there were procedures for vetting any candidate signal, checking it against every possible source of instrumental artifact, running it past the entire collaboration, having external reviews scrutinize the data. This process took about 5 months. On February 11, 2016, the LIGO collaboration announced the detection. In the preceding months, several hundred people had known what was found and kept it quiet, which is its own kind of remarkable thing. 3 of the people most responsible for making the detection possible, Kip Thorne, Rainer Weiss, and Barry Barish, shared the Nobel Prize in Physics in 2017. The citation mentioned the detection of gravitational waves and the observation of the merger of binary black holes. Both halves of that description were firsts in the history of physics. The Nobel Committee sometimes moves slowly. In this case, they moved within 2 years of the detection, which by their standards is almost fleet-footed. Since that first detection, LIGO and its partner Detector Virgo in Italy have recorded dozens of gravitational wave events. Binary black hole mergers at various masses and distances. Binary neutron star mergers, one of which was simultaneously observed in light across the entire electromagnetic spectrum, from gamma rays to radio waves, in a moment of multi-messenger astronomy that opened a new era in how we observe the universe. Black hole neutron star mergers. The catalog of events is growing, and each one is a test of general relativity in extreme conditions, and each one passes. That's one form of direct contact with black holes. The other is imaging them, and it required a completely different approach. The challenge of imaging a black hole is one of angular resolution. For all the drama of gravitational wave detection, at least the signal itself arrives at Earth in a manageable form. A gravitational wave from even a relatively nearby event might distort the LIGO arms by a detectable amount. But photographing a black hole means resolving spatial structure that's extraordinarily small, as seen from Earth. Even the largest black holes in nearby galaxies subtend angles on the sky of only tens of micro-arcseconds. A micro-arcsecond is 1/1,000,000th of an arcsecond. An arcsecond is 1/3600th of a degree. We're talking about the angular size of an orange sitting on the surface of the moon. No single telescope built on Earth, and no space telescope yet launched, can resolve structure at that scale. The technique that makes it possible is called Very Long Baseline Interferometry, or VLBI. The idea is to use multiple radio telescopes spread across enormous distances and combine their signals in such a way that the resulting angular resolution is determined not by the size of any individual dish, but by the distance between the most widely separated dishes. The resolution depends on the ratio of the wavelength of the radiation you're observing to the baseline, the distance between the farthest apart telescopes. If your baseline is the diameter of the Earth and you're observing at radio wavelengths in the millimeter range, you can in principle achieve the resolution needed to see structure at the micro-arcsecond level. In principle, the practical challenges are enormous. You need to synchronize the clocks at all the participating telescopes to better than a fraction of a picosecond, a trillionth of a second. You need to record vast amounts of data and ship hard drives across the world to be correlated at a central facility, because the data rates are too high to transmit in real time. You need atmospheric corrections and careful calibrations and enormous computing power. The Event Horizon Telescope project linked together radio observatories spanning from Hawaii to the Chilean Andes to the South Pole, effectively creating a telescope with a baseline equal to the Earth's diameter. The primary target was the supermassive black hole at the center of a galaxy called M87, Messier 87, a giant elliptical galaxy about 55 million light-years from Earth containing a black hole with roughly 6.5 billion times the mass of our Sun. This is a black hole so massive that the entire solar system out to the orbit of Neptune would fit within it with room to spare. The Schwarzschild radius is enormous in absolute terms, but the distance is 55 million light-years, so the apparent size on the sky is still tiny. The observations were made in April 2017. The data was so voluminous that it couldn't be transmitted electronically. It had to be physically shipped on hard drives, including hard drives from the South Pole Telescope that had to wait until the Antarctic winter ended before they could be flown out. The correlation and imaging process took nearly 2 years. And in April 2019, the image was released. It showed a bright ring of emission surrounding a dark central region. The ring is the accretion disk, superheated gas, and plasma swirling around the black hole at relativistic velocities, heated to temperatures of billions of degrees and glowing in radio emission that, when imaged at the wavelengths the EHT used, appears as a blurred but structured ring. The dark shadow in the center is where the black hole's gravity is so strong that no light can escape, and no light from behind can make it through to us, leaving a silhouette. The size and shape of that shadow are predictions of general relativity. Given the mass of the black hole, the theory tells you precisely how large the shadow should appear. The image matched the prediction. The photon ring, the ring of light produced by photons that have orbited the black hole one or more times before escaping outward, was where it should be. The shadow diameter was consistent with the mass independently estimated from stellar orbits in M87's core. A few years later, the Event Horizon Telescope released a second image, this one of the supermassive black hole at the center of our own galaxy, Sagittarius A*, which sits about 26,000 light-years from Earth and contains about 4 million solar masses. Imaging Sagittarius A* was in some ways harder than M87 because it's a less massive black hole with a smaller event horizon that changes on shorter timescales, making the imaging process more complicated. But it worked. We now have images of two black holes. Both look, broadly, like what general relativity predicted. Both have the characteristic ring shadow structure. We have moved, within a remarkably short time, from black holes being theoretical constructs to hearing their collisions to photographing their shadows. It's a good century of work. But I want to stay for a while with something that the straightforward triumphant narrative of these detections can obscure. Because alongside the confirmations of general relativity, the theory is also pointing at things we genuinely don't understand. And one of the deepest of those things connects back to a discovery made in the 1970s that started with a question you might not have expected. Does a black hole have a temperature? The answer, before you think about it, seems obviously no. A black hole, in the classical general relativistic description, is a perfect absorber. Everything goes in, nothing comes out. A classical black hole has no temperature in the thermodynamic sense. It radiates nothing. Its temperature would be absolute zero. End of story. But in the early 1970s, a young physicist named Jacob Bekenstein, working at Princeton under John Wheeler, proposed something that seemed outrageous. He argued that black holes have entropy. Entropy is a measure of the number of possible microscopic states consistent with the macroscopic description of a system. It's a measure of disorder, in a rough sense. And in thermodynamics, entropy and temperature are inseparable. A system that has entropy must have a temperature, and a system that has a temperature must radiate. So if Bekenstein was right, black holes must radiate. But black holes don't radiate. That's the whole point. So Bekenstein must be wrong. That was Stephen Hawking's initial reaction when he heard Bekenstein's proposal. He set out to prove it wrong. He applied quantum field theory, the framework that describes quantum mechanical behavior of fields in spacetime, to the region just outside a black hole's event horizon. And what he found surprised him. Bekenstein was right. Not quite for the reasons Bekenstein had originally argued, but right nonetheless. Black holes do have a temperature. They do radiate. The mechanism is quantum mechanical in origin, and it has to do with what quantum field theory says about the vacuum. In quantum field theory, empty space is not really empty. The vacuum is a seething, fluctuating state in which pairs of particles and their antiparticles are continuously popping into existence and then annihilating each other. These are called virtual particle pairs. They borrow energy from the vacuum, exist for a fleeting moment constrained by the uncertainty principle, and then annihilate and return the energy. This happens everywhere, all the time, and ordinarily leaves no trace. But near the event horizon of a black hole, something different can happen. One member of the pair can cross the horizon and fall into the black hole while the other escapes outward. The escaping particle carries real energy away from the black hole. The black hole must lose a corresponding amount of mass to compensate. From a distance, the black hole appears to be emitting radiation, a faint thermal glow whose temperature depends inversely on the black hole's mass. This is Hawking radiation. The temperature of Hawking radiation from a black hole of stellar mass, say 10 solar masses, is about 6 billionths of a Kelvin. That's colder than anything in the known universe, colder than the cosmic microwave background radiation that fills all of space and has a temperature of about 2.7 Kelvin. So in practice, stellar mass black holes are absorbing far more from the cosmic microwave background than they are emitting through Hawking radiation. They are growing, not shrinking. The evaporation due to Hawking radiation would only dominate for isolated black holes in a universe much colder than ours, which will eventually happen but is not happening now. And even then, the timescale for a stellar mass black hole to evaporate completely is on the order of 10 to the 6 to 7th years. A 1 followed by 6 to 7 zeros. The current age of the universe is about 14 billion years, which in scientific notation is roughly 10 to the 10. So the evaporation timescale is enormously, almost incomprehensibly longer than the current age of the universe. But here's where the physics becomes genuinely troubling in a way that hasn't been resolved in the half-century since Hawking made this discovery. Hawking radiation is thermal. It's random. It carries information about the temperature of the black hole but nothing else. It tells you nothing about what fell into the black hole to create it. Nothing about the book you threw in, or the star that collapsed to form it, or the protons and neutrons and quarks that it's made of. If the black hole eventually evaporates completely, all of that information is gone. The radiation that's left is featureless. And in quantum mechanics, this is not allowed. One of the deepest principles of quantum mechanics, called unitarity, says that the quantum state of a system evolves in a way that preserves information. Given the final state of a quantum system, you can in principle reconstruct the initial state. Information is never destroyed. The universe keeps perfect records. Always. But if a black hole can form from a specific collection of matter containing specific information and then evaporate into featureless thermal radiation, the information has been destroyed. The initial and final states are not connected by any quantum mechanical evolution. The universe has forgotten something. This is the black hole information paradox. Hawking himself believed for decades that the information was genuinely destroyed, that black holes were a phenomenon that forced a revision of the unitarity principle of quantum mechanics. Most physicists working in quantum theory and string theory disagreed. They believed information was preserved, somehow encoded in the outgoing Hawking radiation in some extraordinarily subtle and scrambled form that Hawking's original calculation missed. The calculation, after all, was approximate. It treated the black hole as a fixed background and didn't account for the back reaction of the radiation on the geometry. Perhaps a more complete calculation would reveal that the radiation is not truly thermal, that it carries tiny correlations encoding the initial information. In 2004, Hawking announced at a conference in Dublin that he was conceding the argument. Information was probably preserved, he said. He conceded a bet he'd made with Caltech physicist John Preskill years earlier, presenting Preskill with an encyclopedia of baseball as the prize, in the spirit of returning information in a disordered form. It was a characteristically wry moment. But the concession came without a mechanism. He could accept the conclusion without being able to explain how. And that's essentially where things still stand. The most influential proposal for how information might be preserved involves something called the holographic principle. The idea has its roots in Bekenstein's original observation about black hole entropy, the observation that Hawking had set out to disprove and ended up confirming. Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck length squared. Not the volume inside the black hole. The area of its surface. This is deeply strange. For any ordinary system, entropy scales with volume. A box of gas twice as large has roughly twice as much entropy, because the number of possible microscopic states scales with the amount of stuff, which scales with the volume. But for a black hole, entropy scales with surface area. The number of distinct possible internal states of a black hole is determined by the area of its boundary, not by anything inside. This suggests that all the information about what's inside a black hole is somehow encoded on its surface. The interior is like a holographic projection of the boundary. Gerard T. Hooft and Leonard Susskind generalized this into the holographic principle, the conjecture that any quantum theory of gravity in a given volume of space is equivalent to a quantum theory without gravity living on the boundary of that region, encoding all the same information in one fewer dimension. Think about a hologram, where a three-dimensional image is encoded on a flat two-dimensional surface. The holographic principle suggests the universe might work something like that at a fundamental level. That everything you experience as a three-dimensional world, with its contents, its history, its quantum states, might be fully described by a theory living on a distant two-dimensional surface. The interior of the universe as a holographic projection of its boundary. This idea found its most precise mathematical formulation in the ADS our CFT correspondence, proposed by Juan Maldacena in 1997, which is one of the most cited papers in all of physics and which establishes a precise mathematical equivalence between a certain type of quantum gravity theory in a certain type of spacetime and a quantum field theory without gravity living on that spacetime's boundary. It's not exactly our universe. The specific spacetime geometry in the Maldacena correspondence is not the geometry we live in. But it's a proof of principle that the holographic encoding of information is mathematically consistent, and that bulk physics can indeed emerge from boundary physics. And it's been enormously productive as a tool for understanding quantum gravity and strongly coupled quantum field theories. The information paradox and the holographic principle are at the absolute frontier of theoretical physics. They point toward the great unfinished project. Because general relativity and quantum mechanics are the two pillars of modern physics, and they don't agree with each other. Not approximately. Not in detail. Fundamentally. General relativity describes gravity as smooth, continuous curvature of a four-dimensional spacetime. Quantum mechanics describes the other three fundamental forces, electromagnetism, the strong nuclear force, the weak nuclear force, as being mediated by discrete particles, photons, gluons, W and Z bosons, each with quantized properties, governed by the probabilistic mathematics of quantum field theory. Both frameworks are spectacularly successful in their own domains. General relativity has passed every observational test we've devised for a century. The standard model of particle physics, built on quantum field theory, correctly predicts properties of subatomic particles to extraordinary precision. And yet when you try to combine them, when you try to write down a quantum theory of gravity, you get infinities. The mathematics breaks down. You get nonsensical answers. The theories refuse to talk to each other in the regime where both should apply, which is the regime of the very dense and the very small, the center of a black hole, the first instant of the Big Bang. String theory is the most developed attempt at a theory of quantum gravity. It proposes that the fundamental constituents of nature are not point particles but tiny one-dimensional objects, strings, that vibrate in different modes, with each mode corresponding to a different particle type. At low energies, the theory reproduces the standard model and general relativity. At high energies, near the Planck scale, the stringy nature of the fundamental objects resolves the infinities that plague conventional quantum field theory approaches to gravity. String theory also predicts extra dimensions of space, curled up at scales too small to detect with current technology. It predicts supersymmetry, a symmetry between particles of different types called fermions and bosons. It has produced mathematical tools and insights, including the ADS or CFT correspondence, that have proven useful even outside of string theory proper. But it has not yet produced a unique, distinctive prediction that experiments have been able to confirm or rule out. There are too many possible versions of the theory, corresponding to different ways the extra dimensions can be curled up, and no clear mechanism for selecting which version describes our universe. Loop quantum gravity takes a different approach. Rather than replacing the fundamental constituents, it starts from general relativity and tries to quantize it directly, treating space-time itself as made of discrete chunks at the Planck scale. The theory predicts that space, at its finest grain, is not smooth and continuous but made of a network of discrete units. That there's a minimum possible length, about 10 to the minus 35 meters, below which the concept of distance loses meaning. Loop quantum gravity has had some success in addressing the singularities that appear in classical general relativity, suggesting that the singularity at the center of a black hole or at the Big Bang might be smoothed out into a finite, extremely dense region in a quantum description. But like string theory, it has not yet produced clearly testable predictions that current or near-future experiments can reach. This is the frontier. Open, unresolved, genuinely contested. The smartest people in theoretical physics have been working on quantum gravity for 50 years and we don't yet have a definitive answer. That's not a criticism of those people. It's a reflection of how hard the problem is. It may require new experimental data that we don't yet have access to. It may require conceptual insights that haven't yet occurred to anyone. It may require a revision of ideas so fundamental that even framing what needs to change is difficult until someone finds the frame. But here is what I want to leave you with, because I think it's easy to lose it in the excitement of the frontier and the open problems. Look at how far we've come. We started with a man imagining himself falling off a roof in 1907 and asking what he would feel. That question, pursued with patience and stubbornness and mathematical courage across a decade of wrong turns and competition and personal difficulty, produced the field equations of general relativity in November 1915. Those equations contained, implicitly, the prediction of gravitational waves, the prediction of black holes, the expansion of the universe, gravitational lensing, gravitational time dilation, which operates in the GPS satellites right now as you lie here, dark energy, the dominant component of the universe's energy content, and more, still being explored. The equations were written on a chalkboard in Berlin while the world was tearing itself apart in the First World War. And they have been passing experimental tests ever since. One by one, slowly at first and then faster, as our instruments improved. Mercury's precession, the bending of starlight in the 1919 eclipse, the gravitational redshift measured in laboratories and in GPS systems, the direct detection of gravitational waves in 2015, the imaging of a black hole shadow in 2019. Each test passed. Each prediction confirmed. The theory is a century old and still collecting evidence in its favor. What makes that extraordinary is not just the precision of the confirmations. It's what they represent about the relationship between human thought and the structure of the universe. The curvature of space-time, the geometry of the gravitational field, the behavior of light near massive objects. These are not things you could have observed directly in 1915. They were mathematical consequences of two postulates and a decade of work. They lived in equations on paper before they lived in any instrument. And the universe turned out to actually work that way. The equations were describing something real. Not approximately real, not metaphorically real. Precisely real, in the way that only becomes clear when you build instruments capable of measuring the actual numbers. That's the thing about physics that is easy to say and hard to really sit with. It works. The correspondence between mathematical structure and physical reality goes so deep, and is so consistently confirmed, that it sometimes seems almost miraculous. There's no obvious reason why the universe should be describable by equations at all. There's no logical necessity that a question about falling, turned into differential geometry by a physicist who had to learn the mathematics as he went, should correctly predict the merger of black holes a billion light-years away. And yet, the waveforms match. The shadows are where they should be. The orbits precess by exactly the predicted amount. Whatever Einstein was doing in that decade of struggle, whatever Schwarzschild was doing in the trenches of the Eastern Front working through the field equations in his spare moments, whatever Penrose was doing with his trapped surface theorem in 1965, they were finding real things about the actual universe. Not conventions, not useful fictions, not approximate models that break down when pushed. Real things. And the remarkable corollary is that what we don't yet understand is also real. The center of a black hole, where the curvature becomes infinite and the equations break down, is not a mathematical artifact. It's pointing at something that actually happens, or at the limits of a framework that needs to be extended. The information paradox is not a philosophical puzzle about the meaning of probability. It's a conflict between two enormously successful theories that tells us one or both of them needs revision at some level we haven't yet identified. The nature of dark energy, the cosmological constant that Einstein introduced and abandoned and that turned out to be the dominant component of the universe's energy budget, is not an inconvenient term in an equation. It's a real physical thing that is actually out there, actually driving the acceleration of the universe's expansion, and we don't know what it is. These open questions are not embarrassments. They are invitations. They are the universe pointing at the next place that careful thought, carried far enough, will reveal something unexpected and beautiful and real. Einstein built on Riemann, who built on Gauss, who built on Euler and Newton and Galileo. Whoever eventually resolves quantum gravity will build on Einstein. The structure of understanding is cumulative. Newtonian gravity is not wrong. It's a limit of general relativity, accurate in the regime of slow speeds and weak fields where it's been applied for centuries. General relativity is probably not wrong either. It's probably a limit of whatever comes next, accurate in the regime where quantum effects on spacetime are negligible, which is essentially all of the universe we've directly observed so far. The next theory will contain these as special cases. The larger circle contains the smaller ones. And you know, lying here, letting all of this settle, there's something worth holding on to beyond the technical content. It's the scale of the human effort and the scale of the ideas. That people, in ordinary human bodies, with ordinary lifetimes, with space-time curving around you right now, rivalries and health problems and the background noise of history happening around them, the same geometry is operating on you and on the Earth and on the Sun and on the supermassive black hole at the center of our galaxy and on the gravitational waves exact solution to universe right now from mergers that happened billions of years ago, quietly working through the topology of trapped surfaces, and we're in the middle of slowly learning to read singularity. We've been doing it for a little over a century, and we can already hear black holes building an instrument to hear something that think about where another century will take us. All of this is continuous. What instruments will exist. All of it is the same human impulse, and what same questions the answers will open up, and how strange and can't understand something if we think carefully enough. Let that be the last same patience that sits with a hard problem, not the equations or the names or the dates. Just that. The universe has a deep structure, and it yields, slowly and with difficulty, but it yields to the patience of someone willing to sit with it long enough. Someone willing to ask what it feels like to fall. Everything else follows from there. Actually, let's go back. Because there's something we move through too quickly, and it deserves its own space. We talked about general relativity predicting the bending of light and about the 1919 eclipse expedition that confirmed it. But we didn't really sit with what that confirmation meant, what it felt like, or how uncertain and contested it actually was at the time. Because the story that's usually told, Einstein predicts something, Eddington confirms it, the world cheers, is a clean narrative that happens to be roughly true at the level of headlines but significantly more complicated at the level of actual events. And the actual events are more interesting. Let's go back to 1916. Einstein's field equations are complete. He's already applied them to Mercury's perihelion and gotten the right answer. Now he turns to the light-bending prediction, and he works out the general relativistic prediction with care. Starlight passing close to the edge of the sun should be deflected by 1.75 arcseconds. An arcsecond, remember, is 1/3600th of a degree. So we're talking about an angle considerably smaller than anything visible to the naked eye. The deflection is tiny in absolute terms, but it's measurable, in principle, if you can observe stars near the sun, which you can only do during a total solar eclipse when the moon blocks the direct sunlight. And there happened to be a total solar eclipse coming, in May 1917. Einstein was already writing to astronomers about the possibility of testing the prediction. Here's what made this particular test so clean and decisive in concept, even before we get to the practical difficulties. Newton's theory of gravity could also be used to derive a prediction for light bending. If you treated light as composed of particles with some effective gravitational mass, you could calculate how much the sun's gravity would deflect a passing light beam. The answer from Newtonian gravity is about 0.87 arcseconds, exactly half of Einstein's general relativistic prediction. So the eclipse test wasn't just about whether light bent. Both theories predicted it would. The test was about whether it bent by the Newtonian amount or twice the Newtonian amount. And that factor of 2, that clean doubling, came from something specific and elegant in the general relativistic calculation. The extra deflection in general relativity, compared to Newtonian gravity, comes from the curvature of space, not just the gravitational effect on the energy of the light. In Newtonian gravity, space is flat, and the deflection comes purely from the gravitational potential well that the photon traverses. In general relativity, space itself is curved near a massive object, and a photon traveling through curved space follows a curved path even without any explicit gravitational force. The spatial curvature contributes an additional deflection equal in magnitude to the Newtonian prediction, doubling the total. It was a test of whether space itself was curved, not just whether gravity could deflect light. Now, the practicalities. The eclipse of May 1919 was visible from a narrow band crossing the South Atlantic. 2 expeditions were organized. One went to the island of Principe off the west coast of Africa, in what was then the Gulf of Guinea, led by Arthur Stanley Eddington and a colleague named Edwin Cottingham. The other went to the town of Sobral in northern Brazil, led by Andrew Crommelin and Charles Davidson. Eddington was a natural choice. He was one of the few physicists outside of Germany and the Netherlands who had read and understood general relativity in depth. A Dutch physicist named Willem de Sitter had been sending Einstein's papers to England during the war years, when scientific communication between Britain and Germany had largely broken down. Eddington received them, worked through the mathematics, and became the theory's chief advocate in the English-speaking world. He was also, as we mentioned, a Quaker and a conscientious objector, a status that had nearly resulted in his being compelled into military service during the war. His colleague Frank Dyson, the Astronomer Royal, had intervened on his behalf, arguing that Eddington's scientific work was of sufficient importance to justify an exemption. The eclipse expedition was partly the result of that argument, a demonstration that Eddington was engaged in important science.